Welcome back to another explainer. Look, today we are tackling a massive, incredibly frustrating headache that literally every lab scientist knows all too well. We're talking about troubleshooting ELISA hook effects and low sensitivity. If you've ever spent days carefully prepping a run, carefully pipetting your samples, only to end up with wasted plates, wonky standard curves, and absolutely zero usable data, I completely feel your pain. I've been right there at the bench, staring at the plate reader in absolute disbelief. But today we are going to fix it.
So, let me ask you something. Have your highest concentration samples ever mysteriously reported as completely negative? I mean, you know the biology is real, your rationale is incredibly strong, yet your patient or study samples look suspiciously perfectly normal. It's wildly frustrating, isn't it? You naturally start questioning everything, your reagents, your pipetting technique, maybe even your entire career choice. But what if the assay isn't failing because it's poorly built? What if actually it's just completely overwhelmed?
Okay, let's dive right into this. Here is our agenda for the explainer today. We'll start with 1. The assay bench reality. Then 2. Diagnosing the hook effect. 3. The 5 sensitivity knobs. 4. Step-by-step assay fixes. And finally, 5. Designing for method defensibility.
All right, kicking things off with Section 1, the assay bench reality. Or really, when standard curves fail.
Let's talk scientist to scientist here for a second. Immunoassays rarely behave like those perfect textbook examples we see in the kit manuals, right? We're dealing with the messy, unpredictable reality of biology. The textbook, perfectly bell-shaped hook effect is actually pretty rare to catch perfectly on a plate. Instead, what you usually encounter are these incredibly ambiguous failure patterns. Maybe your top standard reads unexpectedly lower than the point right below it, or, bizarrely, your highly concentrated samples actually increase in calculated signal after you dilute them. Wait, what? Yeah, you might see non-monotonic recovery in parallelism experiments, or honestly, the worst one, your top replicates are super precise, very believable, but totally biologically implausible. These aren't just random noise artifacts, guys. These are the real-world symptoms of a failing standard curve.
Which brings us nicely to Section 2, diagnosing the hook effect, seeing the unseen.
It's time to treat this like a real diagnostic mystery. And we're about to solve exactly what's happening inside those tiny wells. The main culprit behind all those weird bench phenomena is the hook effect, which is also frequently called the Prozone Effect. This is a very specific failure mode, where an absolute excess of analyte completely saturates your binding partners. It literally disrupts the proper sandwich formation. It's like a massive traffic jam in your well, driving a false low signal exactly where you expected your highest response to be. I really want to emphasize this point. This isn't just some vague, high-concentration interference. This is a critical design space problem. It means the concentration window where your assay actually behaves linearly is way narrower than you originally anticipated. Now, what's really interesting about this is the massive contrast in how we interpret our assay data. If you're only looking at your fitted standard curves, well, you're probably hiding the problem from yourself. The plate reader software is just trying to do its job by forcing a curve which conveniently masks that signal drop as a simple back calculation error. But look at the raw signal side. This is where the absolute truth lives. Plotting your raw optical density, or luminescence, will immediately reveal a clear downturn or a plateau right at the top. Seriously, always check your raw data before you blindly trust the software's smoothed-out perfect version.
So, why do these standard curves fail at the top end in the first place? Well, it's usually a structural issue with the assay itself. Most commonly, the required analyte range simply exceeds what the assay architecture can naturally support. Development teams often mistakenly and optimistically extend standard curves without rechecking the true binding behavior. Other times, one-step kinetics favor non-productive binding, meaning the analyte binds the detector in solution before ever hitting the solid phase. Or you might just have mismatched capture and detector concentrations. Your incubation and wash conditions could literally be ripping apart your equilibrium. Or maybe an upstream binding problem is just being compressed by your signal system so you can't properly see it.
Okay, let's flip the troubleshooting coin and look at Section 3, the 5 sensitivity knobs, breaking down the signal chain.
What if your problem isn't the top end dropping off, but the bottom end barely registering at all? Low sensitivity in an ELISA rarely comes from just one single bad parameter. Instead, it's a weak link somewhere in your specific signal generation chain. Your bottleneck could be capture antibody density, leading to low capture or steric crowding. It could be detection system efficiency giving you a super weak amplification. Maybe it's your incubation time and kinetics failing to reach true equilibrium. Or sample matrix effects are just physically blocking your epitopes. And finally, it might just be your wash conditions either stripping away your true binding events or leaving behind a frustratingly high background noise.
Let's look a bit closer at your capture optimization range. A standard, safe starting point is typically 0.5 to 5 micrograms per mil. But here's the trap, and we've all fallen for it. Blindly pushing your capture antibody to the highest concentration will not automatically yield more signal. In fact, jumping straight to 5 micrograms per mil often causes severe plate saturation and steric crowding. Basically, the antibodies are packed so tightly together on the plate that they can't even effectively grab the antigen. It's a classic case of more definitely not being better.
And hey, here's a fantastic troubleshooting shortcut for you. 10 to 100 times. That is the massive sensitivity gain you can often achieve simply by switching your detection chemistry. Literally, moving from a standard colorimetric read to a chemoluminescent system can yield an incredible leap in sensitivity without you ever having to touch your antibody concentrations or completely re-engineer your binding kinetics. It's a total game changer.
Let's move along and see how this all builds in to Section 4, Step-by-Step Assay Fixes. This is a protocol you can actually use this week.
We've identified the core issues, and now I want to give you a rigorous, bulletproof path forward. Here is a precise 6-step protocol for the bench. Step 1. Actively flag any signal drops at the top of the curve. Step 2, and honestly this is absolutely crucial, run serial dilutions of those suspect samples. If the calculated concentration goes up after you dilute it, boom, you definitively have a hook effect. Serial dilutions are the absolute fastest and most informative check you can run. Step 3. Inspect those raw signal plots. Step 4. Lower your upper calibration range and stop trying to force it to work. Step 5. Compare 1-step versus 2-step binding to wash away excess analyte. And finally, Step 6. Use DOE screening for interacting variables.
Speaking of DOE, or design of experiments, a structured optimization cycle essentially condenses weeks of incredibly frustrating guesswork into just a few days of highly targeted benchwork. Think about it. Day 1. You map out your potential sensitivity drivers. Day 2, you run a fractional DOE screening on just a plate or two. Day 3, you analyze those factor interactions. And by day 4, you've refined your ranges for the very next cycle. It is an incredibly efficient way to optimize without losing your mind.
And this is exactly why you need to abandon the old one factor at a time method, or OFAT. Just drop it. It's slow, it's highly misleading, and it completely ignores how variables interact with one another in the real world. A higher sample dilution might only solve your problem if you simultaneously increase your detector concentration. DOE evaluates multiple factors simultaneously, revealing those hidden golden combinations that actually control your sensitivity. Look, DOE isn't just some dry statistics exercise. It's a sanity-saving strategy that prevents massive downstream disasters. Let's bring it all home with Section 5, Designing for Method Defensibility, Preparing for Validation. We really need to elevate the conversation right now from simple bench fixes to the crucial realm of regulatory validation. Consider the strict FDA and ICH guidance for ligand-binding assays. They explicitly call for assessing dilution-related behavior and demonstrating that prozone or hook effects do not compromise quantitation. They are literally spelling it out for us. Early troubleshooting isn't just about saving a few plates. It's a strict regulatory requirement for successful method transfer. If you don't fix this now, it is absolutely going to derail your validation down the line.
So the crucial takeaway here is this. You are not optimizing for the highest signal. Don't just chase signal. You are optimizing for a robust, defensible design space. A smaller, well-behaved, strictly defined analytical range is always, and I mean always, better than a broad, sweeping curve that is secretly packed with hidden false low risks.
As we wrap up this explainer, I want to leave you with a bit of a provocative thought. Are you actually validating the true underlying biology of your samples, or are you just validating your software's blind spots? You don't have to lose any more plates or weekends to guesswork. Use the structure steps we just walked through. Always look at your raw data and seriously consider implementing DOE. Now I want to hear directly from you. What's the single most frustrating ELISA bottleneck you are dealing with right now in your lab? Drop a comment below and let's talk about it. And hey, if you found this deep dive genuinely helpful, please make sure to hit that like button, share this with your entire lab team so they stop making these mistakes too, and subscribe to support more practical explainer guides just like this one. Keep experimenting, stay curious, and I'll see you in the next one.